इसमें क्या प्रॉब्लम है? दोनों
Yeah, good morning, students. What happened again today? People are not there. Paras?
Not sure मैम, पता नहीं।
कोई क्लास थी?
नहीं मैम, अभी तो ये फर्स्ट लेक्चर ही है।
अच्छा, तो आना चाहिए था।
हाँ जी मैम।
And how are things going at your
It's great मैम, अभी तो ठीक है मैम। देखो क्या हुआ।
कोई शुरू नहीं हुए है ना?
Yes अभी ठीक है।
I think 5 नवंबर से ही शुरू कर पाएंगे, उससे पहले नहीं हो पाएंगे।
अच्छा मैम, ले लिया सर्वर मैम, खरीद लिया सर्वर?
सर्वर बोल रहे हैं अब आने वाला है, इस वीक में बोला था उन्होंने, तो अब आजकल में पता लगेगा।
अच्छा
कि क्या हुआ। वो कह रहे थे कि 2-3 तारीख तक आ जाएगा एंड देन वील नीड 1 or 2 days फॉर इंस्टॉलेशन। तो उसके बाद में जो लार्जर ग्रुप्स हैं उनको क्विज तब करने के लिए मिलेगा। लेट्स सी, बट आई डोंट नो, एलएमएस की स्थिति बहुत अच्छी नहीं दिख रही है। आई डोंट नो हाउ इट वर्क्स। गूगल अलाउ कर देते तो ज्यादा बेहतर होता।
यस मैम, पता नहीं,
पता नहीं है, आई डोंट नो। उनका भी, मुझे भी नहीं पता कि व्हाट कॉल दे टेक। बच्चे भी आजकल है ना सुस्त हो गए, सर्दी ज्यादा लग।
यस मैम, वो सुस्त भी हो गए, खफा भी हो गया, बहुत चीजें हो रही हैं।
खफा क्यों है?
मैम पता नहीं चलता मैम, पता नहीं चलता ना मैम। तैयारी कर लेते बच्चे एक पर्टिकुलर सिलेबस की, बाद में सिलेबस बढ़ जाता है, फिर बाद में कहते हैं क्या हो रहा है।
सिलेबस नहीं, सिलेबस तो नहीं बढ़ाया हमने।
नहीं मैम, आपका नहीं बढ़ा, हम दूसरे सब्जेक्ट्स का बढ़ गया।
अच्छा, बढ़ गया।
जैसे आईसीटी है हमारा, उसमें पूरा सिलेबस ही आ गया, कहते सारा सिलेबस करो।
अच्छा, वो तो वैसे ही ड्राई सा सब्जेक्ट है, थोड़ा बच्चों को ऐसा ही लगता है। राइट। नहीं, आई थिंक आई विल टॉक टू पीपल एंड एडवाइज देम कि थोड़ा सिलेबस कम कर लें।
सिलेबस थोड़ा सा, क्योंकि वो ये कह रहे हैं कि 3 क्विज लेंगे, तीनों में सारा सिलेबस आ जाएगा। मैं कह हो रहा है।
नहीं, अगर उसको डिवाइड कर लें, यू कैन गिव अ सजेशन, आई विल आल्सो टॉक टू माय फैकल्टी।
हाँ जी मैम, मैंने मेल भी डाला था, मैंने सर को बात भी की थी, लेकिन सर थोड़ा रिजिड हो रहे थे इस चीज पे, तो मैंने फिर आगे डिबेट नहीं की।
कौन से, हेमदत्त के एके सिंह?
एके सिंह।
अच्छा, ठीक है, आई विल टॉक टू माय फैकल्टी, इन जनरल बात कर लूंगी।
थैंक यू मैम। हाँ जी मैम।
ठीक है,
और मैम वो जैम बोर्ड के कुछ बच्चे कह रहे थे कि वो नोट्स अगर आप डाल देते तो काफी हेल्प हो जाती है।
हाँ, मेरे पास है ना, घर पे नेट ने अलाउ नहीं किया मुझे डालने के लिए। मेरे
अच्छा।
एक्चुअली लैपटॉप पे थे सारे लेक्चर, तो
ओके
घर
ओके,
से डल नहीं रहे थे। तो आज
नो इशू।
मैं पेन ड्राइव पे कुछ चीजें तो लेके आई हूँ, तो
ओके
यहाँ पे इंस्टीट्यूट के सिस्टम से डालूंगी।
ओके ओके,
ठीक है, वो थोड़ा कंस्ट्रेंट है। कई बार क्या होता है, ऑफिस में बहुत ज्यादा बिजी हो जाए तो टाइम नहीं लग पाता अपलोडिंग के लिए,
यस
और
मैम,
घर
यस
में
मैम,
उतनी बैंडविड्थ नहीं है। वो एलएमएस पता नहीं, घर से तो कभी अपलोड ही नहीं होता, पता नहीं क्या चक्कर है। हॉटस्पॉट से भी नहीं चलता और घर के वाईफाई से भी नहीं चलता। यहाँ पे इंस्टीट्यूट की बैंडविड्थ फिर भी ठीक है, वहां
यस
से।
मैम, वो वहाँ पे थोड़ा कनेक्शन अच्छा है।
हाँ, बस इसी कारण डिले हो गया। मुझे एक दो बच्चों ने डायरेक्ट मैसेज भी किया था, एंड आई हैड टोल्ड देम कि मैं डाल दूंगी, जितने मेरे पास आए वो डाल दूंगी, बट आई हैव नॉट रिकॉर्डेड ईच एंड एवरी लेक्चर। ठीक है, जितने भी हैं वो डाल दूंगी।
ठीक है, नो इश्यूज, थैंक यू।
if you people can send me particular date wise कि कौन सी डेट को, तो मेरे को रिकॉर्ड ढूंढना आसान हो जाएगा, क्योंकि मुझे पूरा वीडियो देखना पड़ता है बिफोर आई सॉर्ट इट आउट, है ना।
मैं पूछ लूंगा हम बच्चों से एक बारी।
हाँ, बच्चों से पूछ लो कौन सी डेट का। डेट मुझे इंपॉर्टेंट है, नॉट द टॉपिक। टॉपिक से तो मुझे फिर सारे वीडियो खोल खोल के देखने पड़ते हैं।
नहीं
ठीक
मैम,
है, VHDL ऑनवर्ड्स तो मैंने डाले थे, पर
यस मैम, वो
कॉम्बिनेशनल
डाला
नहीं डाला था मैंने, है ना। तो
यस
उसमें से आप मुझे अगर डेट्स बता दोगे कौन सी डेट्स को थे वो लेक्चर, क्योंकि इसमें इतना जूम चंक है मेरे पास रिकॉर्डेड कि कुछ हद नहीं, क्योंकि सारी मीटिंग्स एंड एवरीथिंग इज काइंड ऑफ
रिकॉर्ड, यस मैम,
स्टोर्ड,
यस
है ना। तो इट विल हेल्प मी आउट। आई थिंक 50% के करीब क्लास आ गई है। लेट्स स्टार्ट आउट। आई थॉट दीज आर इम्पॉर्टेंट टॉपिक्स, सो एवरीवन शुड बी हियर। अदरवाइज क्या होता है कि ये चीजें हैं ना, आपको लॉन्ग टर्म में भी काम आएंगी, एंड अपने आप से कई बारी चीजें समझ में नहीं आती। दो आई नो यू आर इंटेलिजेंट पीपल, यू कैन डू इट, बट स्टिल आई रिकमेंड दैट you people join. Okay, so we were talking about finite state machines, and we had done the state diagrams, and we had taken a couple of examples. This state diagram is also known as Venn diagram, and we had taken a couple of examples for it. Now today what I intend to do is, one, how to convert this state diagram into state table. Second thing which we would like to do is how to minimize this state table. Many of you had sent me the solutions for the problem which I had given, but there are some issues almost everywhere. So I am teaching today how do you find out the minimized state diagram, whether you have used a redundant state or not, and use this method, apply on your FSM, and see for yourself. If you had a redundant state, reduce it, and then send me again the reduced finite state machine. I'm sure by doing this exercise, those who have done it, they will learn a lot, and they will not forget it forever. I'm sure about it, because once you do it by hand, it registers to you forever. So how to minimize this? This is what we will do. So we will remove, minimization means removal of redundant states. And obviously, if you reduce the number of states in your machine, you will have a smaller number of bits, maybe. But if you reduce from 7 to 5, you may not result into a reduced hardware. But if you reduce from something 9 to 7, yes, you do reduce a hardware, because the longer is your state code, the larger number of flip-flops are required, and hence the more hardware. So every time you try to reduce the state, you are trying to reduce the hardware, overall hardware in the implementation. And then we will talk about state assignment. By state assignment, I mean binary code to be assigned. How do you assign a binary code to a state? For example, if you had 5 states, you were to choose 5 3-bit codes out of 8 possible codes. So which state should get what code? How do you decide this? Which results in a minimized hardware. So we will talk about rules for that, and we'll try to do minimization of some machine assignment for one machine or something like that. Okay, so now with this, let me take one Moore machine and one Mealy machine for writing the state table. Okay, so first I am taking one Moore machine. Okay, so this time I'm not starting with a problem, because if I take a problem, converting it to a state diagram is takes time, and then we will do conversion. So I'll start with a Venn diagram, and my main emphasis is how do you convert a given Venn diagram to a state diagram. So let's say this is the given Venn diagram with 4 states. These are the 4 states. State A. Now you will recall in a Moore machine, output is the function of state. So we were writing here z is equal to 0. Other way is I can write it this way, state over the output. Okay, so I can write state over the output, state over the output, again state over the output. So I have output as 1 in state C, and in all other states my output is 0, and I'm using 4 alphanumeric names for the states A, B, C, D. And this is when input is 0. So I have one input X and one output Z. So output is written here and input is written on the arrow. Okay, from here, if it is 1, it comes over here. Again, if 0, it retains in the same state. And if it is 1, it comes to the state C. If 1, it continues to be in the same state. If 0, it goes to D. If 1, it continues in the same state, and if 0, it goes there. I'm not saying what is the problem. We are not bothered how we have arrived at this Venn diagram, but this is the given Venn diagram, which is to be converted to the state table. So in state table, you will have entries. First is the present state. Because everything is the function of present state, and next state is also the function of what is the external input. Okay, so this is my present state, and then what is going to be my next state is dependent on my input X. So I say when X is equal to 0, when X is equal to 1, I have 2 columns. And output, which is Z, this is function of the present state. It is independent of the external input X. So this is how we will draw the table. So I have 4 possible states, A, B, C, D, and that is my table complete. Okay, in state A, if X is equal to 0, my next state is A. If 1, my next state is B. If in state B, input is 0, it continues to be in the same state. And if 1, it goes to state C. In state C, if input is 1, it continues to be in the same state. But if 0, it goes to state D. In state D, if 0, it goes to A. And if it is 1, it continues in the same state. So I have filled in the next state for all the current states, and outputs I know when A, in state A my output is 0, in state B 0, in state C again output is here 1, and for D my output is 0. So this becomes my state diagram. Is that clear to everyone? Any doubt in this? Very simple and easy. Okay. Redundancy, there is no chance of redundancy in this state. It's a very small example. Redundancy problem we will take separately. Let's first do the conversion into the state table. Then I'll tell you redundancy rule. Maybe I can mention the redundancy rule that you check out the two rows. If you see for two different states, the next state for the corresponding input is same, okay, and output is also same, then you know these two are redundant and you can remove one of them. Okay, here it's not the case, so you don't see any such thing. Okay, so let's take another example of a Mealy machine. And in this Mealy machine, I use some redundant states, and I'm taking an example with redundant states so that I can explain to you as well using the same example that how do you remove it. Okay, so the example I pick up is again it's slightly bigger. So we have a Mealy machine. Now let me draw the now remember here the output is function of external input as well. So on arrow you indicate input / output. Okay, and let's say if it is 1 by 1, it goes to state D. Now from state B, if input is 1, output is 1, and it goes to another state which is F, and if it is 0, output is 0, and it goes to a state, let's say E, and now I'll work for the two states. For 0, it continues in the same state. For 1, it goes to a new state with output as 0. And let's say this state is C. And from both the transitions are done. From C, if it is 0, it is going to, let's say, B. And let's say for 1, it comes over here with output also as 1. From D, I have not marked the transitions. So if, let's say, input is 1, output is also 1, and it goes to B. For 0, it, let's say, comes over here, 0 by 0. Now for this E state, let's say 0 by 0, and it goes to, let's say, F. I think it is a complete state diagram which I have drawn for some problem, okay? And these are the kind of diagrams I receive when I receive from the kind of beginners, Okay, so you do make some of the redundant states, and let me tell you, here also we have some redundant state. We are not worrying at this point in time, but we will find out from the state table, because finding it from the Venn diagram is much more difficult, but from state table it's very easy to find out. So let's convert it to the state table. Now this state table will be slightly different than Moore machine. In Moore machine, you had next state as a function of inputs, but output was just unique, one. Whatever is the input, output was unique. Here, output is also the function of input. So we will slightly modify the table. Present state. Then we will have next state for 2, x equal to 0, x equal to 1. Similarly, I will have my output z for two conditions, x equal to 0, x equal to 1. That's it. Okay, so you see the change is only at the output stage. Now we will fill in entries for all the states. I have A, B, C, D, E, and F. So A, B, C, D, E, F. Okay, all the 6 states we have written. Now A, when x is equal to 0, it goes to B, and my output is 0 from this transition. For input equal to 1, it goes to state D, and my output is 1. Fine. For B state, for 0, it goes to E with output as 0. For 1, it goes to F with output as 1. In state C, for 0, it goes to B with output as 0. For 1, it goes to D with output as 1. Okay. Now see D, for input equal to 0, it goes to E with output as 0. For 1, it goes to state B with output as 1. Okay. Now let's see E. Yeah. In E, for 0, it remains in the same state with output as 0. For 1, it goes into state F and with output as 1. In state F, for 0, it remains in the same state with output as 0. And for 1, it goes to state C and with output as 0. Okay, so now this is my state table for this finite state machine. Now clear? Or if anyone has any doubt, please raise your hand or write in the chat box or unmute yourself and speak out. Is that okay? Fine. So I assume this, and as such, it is very simple. Now from the table, how do you remove the redundancy? Now a state is said to be redundant or equivalent if every set of input gives you the same outputs and the same next state, then you can say these two states are equivalent. Now, for example, what you will compare is the row entry should be exactly same. See here B. So B can be equivalent if there is any other B. So I see one more B. Now I see next also is same. This is also same. This is also same. So what I find is this state and these two rows are having exactly same entries. Okay, so that means A is equivalent to C. State A is equivalent to state C. That means I can remove one of them. So I'll remove the later one, C, and I will convert it to, and I will merge it with A. So how do you reduce it? You just eliminate this from the state table, and wherever anywhere else, if C appears, that C should be replaced by A. So I have only here as C. So this C will get replaced by A. Okay. You will again check for equivalence. Is there any other equivalence? So let me, yeah. E, now these two also have E. So I need to compare them. This cannot be equivalent. F, so this is also F. So these two can be equivalent, 0, 0, 1, 1. So that means this B and this E are also equivalent. B is equivalent to E. Okay, so I can remove E, and wherever else now E is coming, that E will be replaced by B. So I'll start seeing from here. E, this becomes B, this E becomes B. Rest all is okay. Is that clear to everyone? So what I have is, I had two redundant states. One was C, so this was redundant, and another redundant state was E. So my state machine has only 4 unique states, A, B, D, and F. Okay, so I can have my reduced table by eliminating these two rows, by changing, replacing C by A and E by B, which I have done over here. You, if you wish, you can rewrite in your notebooks. And if you wish, I can even write over here again. I'm writing it over here as a reduced table. This is present state, next state with x0 and x equal to 1, and then z with x equal to 0 with x equal to 1. So I have 4 states, A, B, D, and F. A has B, D, 0, 1. B has B, F, 0, 1. D has in both case B and 0, 1, and F, A, 0, 0. Now I need to convert it to a Venn diagram. So this is my A. Okay. If x is 0, it goes to B. with output as 0. So this is 0 by 0. For x is equal to 1, output is 1 and it goes to D. So maybe this is my D, 1 by 1. From B, if x is equal to 0, it retains in B with output as 0. In B, if I get 1, I go to F state. One by one, input is 1 and output is 1. In D state, if I have x is equal to 0, my output is 0 and I go to B state. Okay. So input is 0, output is 0. If input is 1, output is 1, state is the same. So 1 by 1, also in the same state. Now last state, in F state, if I have input as 0, my output is 0 and I retain in the same state. If my input is 1, I go to state A and my output is 0. So if input is 1, output is 0, but it goes to A state. So this becomes my reduced Venn diagram. Okay. So I like you to try out on your sample, which you had sent to me. Okay. Convert it to the state table and then find out the redundant states, reduce the table and come out with the reduced state diagram. So it's not that if you are doing a problem, okay, you may land up with a very big diagram, not optimizing on states, but it should be a correct and valid diagram. That is more important. If states are redundant, they can be removed by this process. Okay, so there are automation tools also available which do it, but we know, if we know how to do it, we can even do it. For small machines, we can do it manually. For very big machines, yes, manual working becomes difficult when you have 50 states and some 8-10 outputs and multiple 8-10 inputs with which you are working, and your machine is not completely defined machine. Okay, incompletely defined machines are also used. So then it becomes tedious working with the pen. Okay, so that time you look for optimization tools and the software to help you out. Any doubt? Anyone is having any doubt? So now we will talk about the last topic which we said, and state binary code assignment to the state.
मैम
Yes.
मैम ये रिडंडेंट बिट कट करने के लिए आउटपुट भी सेम होना चाहिए?
हाँ, आउटपुट भी सेम होना चाहिए, नेक्स्ट स्टेट भी सेम होना चाहिए. अगर कहीं पे एक भी डिफरेंस है, एक भी बिट का डिफरेंस है आउटपुट में भी, then you cannot cut the state.
Okay.
Okay.
Yes,
and
ma'am.
it is very important that every entry in your row must match with the other row. Okay.
जैसे हम ये C और E का किया है, अगर ये Z वाला 1 0 और 0 1 होता तो कट नहीं कर सकते थे.
तो नहीं कर सकते थे कट, तो ये दोनों डिफरेंट स्टेट ही कहलाते हैं. ठीक है.
Yes ma'am.
Okay, so now we will talk about state assignment. How are you going to assign the binary codes to the various states? There are just two rules which you follow. Rule 1 is, I'm writing here for your convenience so that it gets recorded with you. States having the same next state. Should be assigned a code which vary in 1 digit. Why I am saying so is, yeah, why people have said so is, if they vary only in 1 digit, you can remove that variable and it will reduce the hardware implementation code. Okay. Rule number 2 is,
आपके रूम में भी नहीं था।
Yes,
तो मैं
please.
किचन में आके डाल दूँ।
अंदर की बकेट चाहिए तो वो रखे रखेंगे तुम्हारे लिए। पूरा चाहिए।
yes, please.
इसकी टांगे निकाल दो, ऐसे ढक्कन खोल के डाल दो। ऐसे कर सकते हो, कोई चल नहीं रही है तो क्या?
मैम ही माइट नॉट बी अवेयर ऑफ दैट, मतलब माइक ऑन होगा, उसको ऑफ कर।
हाँ, मेरे से भी आज हो नहीं रहा है, मेरा भी कोई कंट्रोल. Just speak out if the person listens, it's better. Else okay.
मैं नहाने जाऊंगी तो बोल के जाऊंगी, वो कुरियर आने वाला है आज।
Can you please mute yourself?
प्रचेत भाई ऑफ कर ला यार माइक, ऑडिबल है तुम।
Yeah. Second rule is states that are next states to a state should be assigned a code that vary in 1 variable. What does it mean? The first statement says state having, I should write, states having the same next state should be assigned a code which vary in 1 digit. For example, this is A state, this is B state, and for some condition, they both have the next state as C. So these two, we should try to assign a code which vary in 1 digit. This is what the rule number 1 says. Okay. The second rule says if I have a state and for it there are 2 next states, okay, then let's say P, Q, R. So even Q and R, I should try to assign code which vary in 1 digit. Okay. So basically what we get is neighboring states should get a code which vary in 1 digit. That is what we try to do it. Let's now see for our example, what can we do? Now here, if I have this example, I have 4 states. Okay. Now 4 states tells me that I can use a 2-bit code. Okay, so I have 4 possible codes. So which state should I assign what code? Now see, A has these 2 as next state. So these 2 should try to vary, we should try them to vary in 1 digit. Okay. Another thing, these 2 states have the same next state. So they also should vary in 1 digit. Okay, so which means these three, I want them to vary in 1 digit. Okay, this and this should vary in 1 digit. This and this should vary in 1 digit. Okay, so how should I assign? You can assign this 1 1. You can assign this 1 0. And for this I don't have any issue. So leftover code we can assign over here. So I had no condition with these two as well. So I'll put this 0 1 and this can be 0 0. Recall again. What we said was states having the same next state. So these two are having the same next state B. Okay, so these two should vary in 1 digit. So I have picked up 1 1 and 1 0 for them. Second rule was if two states are next state to the same state, which is B and D are next state to state A. So these two also should vary in 1 digit. So I'm assigning here a code 0 1 and here code 1. So again they vary in 1 digit, and leftover code I am assigning to F. Okay. So the neighboring states try to assign gray codes. That is what it means. Okay. Though at times you might find it very difficult if you are working with all possible. For example, here also I had only 4 possible codes. I didn't had any extra code so that I can choose. But somehow it is still okay over here because these, for example, CB, this is the next state to it is either itself or this. So they are varying in only 1 digit. This and this are also varying in 1 digit. So somehow I could make an assignment which works out, but at times it might not work. And therefore you will add on some extra hardware for it. Okay, even the algorithms which is available in the minimization tools utilize these kind of methods or algorithm within the design. Is that clear to everyone? And now using this code, you can convert your table into a binary state table. So for example, if I see this, I don't have, if I will not remember if I go to the next page. So what I'll tell you is over here how to convert it, and you can convert it. So see, A has a code 1 0. So A gets replaced by 1 0. B gets replaced by 0 1. D by 1 1. 0 1 0 1 and F is 0 0. 1 1 0 0. B is 0 1 0 1. F is 0 0 and A is 1 0. Okay, so these alphabets or alphanumeric names of the state will go and they will be replaced by the binary codes. And now this is called a binary state table. Now, if you have the binary state table, how to convert it into a hardware, you try out. Probably, if you wish, I can take it one example through and through, but I can tell you the straight way the procedure. Probably I'll record it and then I think I'll use the next page. That is the only option. Okay, so let's draw our binary state table. We had present state, next state, and then we had output Z. X is equal to 0, x equal to 1, x equal to 0, x equal to 1. And after that, we will draw the excitation table. So A state, which is 1, 0, this was 0, 1, 1, 1. So I can label it Q1, Q0, Q1, Q0, Q1, Q0. Okay. Then in state B, it is 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0. And this output is always 0. This output is 1 in 3 cases, and this is 0. Okay. Now let's say we are using any T flip-flops. So I'll choose the number of flip-flops required. Since I have a 2-bit state code, so I need 2 flip-flops, 2 T flip-flops. So I need to draw excitation table for T1 and T0. Okay. Now T1 and T0, I will need to do it for x is equal to 0. I'll need to do it for x is equal to 1 in both cases. Okay, so this is for x is equal to 0, for x is equal to 1, again T1 and T0. Okay, so this will also become function of x. What is going to be my T? I will have x as one variable and then I will have another variable. So see here, present state compare with the next state. So my both the bits are changing. So this is 1, this is 1. Here 0, 1. No change, 0, 0. Here no change, this changes. Here this changes, this does not change. And from here to here, first bit changes, second does not change. Here to here, no change. And from here to here, first bit changes, second does not change. Okay, so I have obtained this. Now what will I do? I can make the K-map. I have 3 variables, Q1, Q0, and X as my variable. So I'm using X over here. X is 0, X is 1. And this is my Q1, Q0. So for 0, 0, 0, 1, 1, 1, 1, 0. Now see, they are not in order. So I should fill them at appropriate location. Okay. So first thing, let's say we are doing it for T1. I am doing finding a minimized expression for T1. So in T1, see, this is x equal to 0. So these 4 entries will correspond to x equal to 0 here. Now this is 1, 0. So 1, 0 is this. Okay. So here my T1 is 1. Okay. 0, 1. My T entry is 0. So I'll fill in 0 here. For 1, 1, this is 1. So this becomes 1. And for 0, 0, it is 0. So I'll fill in 0. Okay. Now this is the row for x is equal to 1. And T1 corresponds to these 4 entries. So again, 1, 0 is 0. So I fill in here 0. 0, 1 is 0. So 0, 1 is 0. 1, 1 is this 1. And this 1 corresponds to 0, 0. So this is 1. So this is what I get the K map. So you can find out this is one pair, this is second pair, and this is an isolated one. So you can find what is T1 equal to as a function of Q1, Q0, and X. Find it out. Similarly, you can draw the K map. Again, here X, Q1, Q0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. These entries cannot change. These positions I have to identify accordingly. Okay, so now this first for 0. So 1, 0 is 1 and all 3 are zeros. For this 1, 0 is 1 and 0, 1 is also 1 and these two are 0. Again, this is an isolated one and this is a pair. So you can find out T0 is equal to x dot q1 bar dot q0 plus this x is don't care has gone away and this becomes q1 dot q0 bar. Similarly, you can write it over here x dot q1 bar dot q0 bar plus this pair is q1 q0 plus this pair is x bar dot this is 1 so q1. Okay, so you have the two expressions. Now what are you going to do? You had two T flip-flops. This is what we had chosen. These T flip-flop can be positive edge triggered or negative edge triggered. I'm picking up here positive edge triggered. So this becomes the clock. This is T1, let's say, and this is T0. So flip-flop 1, flip-flop 0. So you design whatever is the circuit required using this is your Q1, Q0. So input to this is Q1, Q0 and also X. Okay, similarly here you will have the input Q1, Q0 and the third input is the same X and you will generate T0. So you can make the optimized network of gates, whatever is desired, and you have done. Now, in addition to this, you also need to have the Z. This is Z. I need to find out the third K map for Z. Again, X, 0, 1, and this is Q1, Q0, which is 0, 0, 0, 1, 1, 1, 1, 0. See, X is equal to 0, all Z's are 0. So these 4 entries are 0. In X is equal to 1, only one entry is 0, which corresponds to 0, 0. So this is 0, these 3 are 1. So I make 2 pairs. So my Z is equal to X dot, this is Q0 plus X dot this, which is Q1. So, or you can say X Q0 plus Q1. Whatever way you want to do it, you can do it. Whatever expression you want to do. So you need a OR gate and a AND gate, or here you need two AND gate and a OR gate, or you can even say implement it using multiplexer as well and do it. So here you will also have another combinational logic. These are combinational logics. 1, 2. I'm coming to your question in a minute. It has input Q0, Q1, and obviously also X. And this gives you Z. Oh, yeah. Thank you for a reminder. I didn't realize. When I start doing a design, I forget the time. Okay, thank you. Anyway, I have finished doing it as well. So I am stopping sharing the screen.
इस पर पढ़े फिर मैं फुल बढ़िया रख लूं ताकि सूख जाए.
हाँ जी
बिल्कुल
बोलो.
साफ है.
Okay. Thank you.
Thank you, ma'am.
Okay, so if there are any questions, we can take up in the next session.
No issue.